right, so chapter 10, really there's no the distinction between the chapters for this whole beginning section is really arbitrary. It's all still just the continued study of heat and thermodynamics. The main summary of chapter 11 is we are going to look at the energy itself and the way it is transferred, and also the thermal processes objects go through as that energy transfers into and out of it. So, whoops, back up. Nope, missed that too. Phys1510, spring 2020. There we go, that's better. Okay, so, chapter 11, more thermodynamics, just continuing the same things. So, thermodynamics is the study of thermal energy and what objects do when they have it. Now, in studying those things, there's an important distinction that needs to be made between internal energy, the energy that the object possesses within itself, and heat as a process. Internal energy is the energy that the entire object possesses within itself. So, very straightforward definition. And we use uppercase U for that variable. So, internal energy equals 3/2 times N, which is still number of moles, so the amount of material that is present, times R, which is still a constant, 8.31, times T, which is temperature in what scale? Very good. So this formula tells you the amount of thermal energy that is inside of the object that is in solid state. That is different to heat. So the internal thermal energy possessed by an object is technically a different phenomena to heat. In English vernacular, we use heat somewhat differently to how we use the word in physics. In physics, heat is defined as the exchange/transfer of thermal energy. So heat is not the thermal energy itself. It is the transfer of thermal energy. It's less of a noun and more of a verb. So it's a process, not a thing. Why does my R look like an L? That's hard. So, technically speaking, we need to describe heat as a process, which even in my own head is a mistake I make a lot because we're just used to thinking of heat as the energy itself. If something has a lot of heat, it is hotter. That's just the way the English language uses the word on average, but technically it is a process, and you calculate that process with this formula. So Q, uppercase Q, is the variable we use for heat, the transfer of thermal energy. And both of these are talking about the energy of an object. This is the energy that is already inside of the object at a specific temperature. N tells you the amount of substance present, so the atoms present, and then this is the temperature of those atoms. So N refers to the amount of thing, T is the temperature of the thing. This formula also cares about the amount of stuff present, but this formula uses the mass of the object instead. So, the heat that an object is either acquiring or losing, because in thermal processes you can either gain thermal energy or lose it. So Q just represents the change in thermal energy. The heat something is gaining or losing is equal to its mass times this constant C times the change in its temperature. Because if you are gaining or losing thermal energy, your temperature must be changing. So it has to be delta T. Because it is delta T, you can use Kelvin or Celsius, because the delta is the same for either scale. So this is a Celsius-friendly formula. So What do you think C is?
Specific heat.
Specific heat, very good. So the M just cares about the mass of the object, but you could have a kilogram of feathers and a kilogram of steel. Are those two piles of objects going to heat up the same way? Are they the same kind of object, even if they have the same mass? No, they have different thermal properties. And the C variable there is what summarizes the thermal property of the type of object you are looking at. So C is a constant called specific heat, and it specifically describes how a specific substance changes temperature when you add thermal energy to it. This formula is just the previous one rearranged slightly. So this is how you calculate specific heat, and the other formula is how you can use specific heat to find the change in thermal energy of an object. So, looking at the orientation of C, C is defined as, the triple equal sign means defined as, so it's even stronger than equal to. It's not that it happens to be the same, it's this is literally defined as this. So C is defined as the change in thermal energy of the object divided by its mass and its change in temperature. As a result, the units of C, so the units that we like to use for C, what is the unit for energy that we like to use in physics? Joules. So for energy we have joules, for mass we have kilograms, and for temperature we have degrees Celsius. You could also use kelvins because the change in Celsius is the same as the change in kelvins. So because every different material has a different specific heat capacity, you don't have to memorize any of them. The tables exist and are available to you, and because they are known constants, you can usually just safely look them up. They are things that are assumed to be known. You have access to the knowledge. It's in your book. You can Google it, frankly. If you know the material, you can assume you know its specific heat capacity. So you will either be given the information, or the problem will be you need to determine specific heat capacity and then determine what the object is made of. There are scientists who use this method to determine what something is. You can heat up a rock to basically and notice, its change in temperature to determine its specific heat capacity, and then figure out what the rock is made of. So this is useful in identification sciences. Now, every object, every material type that has a different C value reacts differently to thermal energy being added to it. Things can either have a rather big specific heat or a rather small specific heat. So, an example of what that sort of represents. Say it's summer and you're heading to the pool. And you step out of your car. Actually, no, let's change it slightly. You're heading to the beach. Because when you get out of the car at the beach, there's sand everywhere. Odds are you've already got your flip-flops off. So you get out of the car, bare feet, and you step on the concrete. Why is that a mistake? Okay, so the concrete is very hot, summer day, beating sun, hot air, uncomfortable. So you immediately cartoon jump 3 feet to your left, and now you're standing on grass. Why is the grass better than the concrete?
Because there's water in the grass.
There is water in the grass, and the grass is a lower temperature than the concrete, usually. It does not burn immediately. But the thing is, both the concrete and the grass are exposed to the same temperature air and are getting the same amount of radiation from the sun. So why would they be at different temperatures?
Grass's specific heat is higher.
Grass's specific heat is higher than concrete's. If something has a higher specific heat capacity, that means it needs more thermal energy to increase its temperature by the same amount. So things with a bigger C actually heat up slower. Well, more specifically, they're still gaining the same amount of thermal energy, but their temperature increases more slowly. And It's less so that grass has a high specific heat capacity and more so that the water in the grass has a high specific heat capacity. So here is a list of common specific heats, and just a cursory glance at this entire table here reveals that water has the biggest specific heat on the table. Out of every material represented here right now, water heats up the slowest. Water has one of the higher specific heat capacities, frankly, in the known universe, which is good, because if it didn't, the oceans would boil from direct sunlight. So it's a good thing. Again, water's unique properties, the fact that it expands when it freezes and has a high specific heat capacity, are two of the things that make life on this planet possible. So it's a very good thing that water is actually an anomaly within the universe. And it's a good thing Earth has so much of it. So, high specific heat capacity, you heat up rather slowly. Conversely, if you look at all of the metals on this table, so aluminum, especially cadmium, copper, germanium, gold, especially gold, these all have very low specific heat capacities. Actually, lead is the lowest here. I didn't realize that before. So, and silver and tin also very low specific heat capacities. So, when it's a very low specific heat capacity, the same amount of thermal energy increases its temperature faster. And so those materials heat up quickly, and concrete is not on there, but concrete is a stone compound, and stone compounds are metallic compounds. So since it's technically made of metal, it heats up quickly too. Same reason why when you get in your car again after a hot summer day and you reach for your seatbelt, the plastic is an okay temperature because it's made of carbon, and carbon has a high specific heat capacity, but the metal of the buckle clip hurts because that's, again, the same thermal energy coming in from the sunlight increases its temperature faster. And specifically for gold, its C is so low that the thermal energy from your hand increases its temperature fast enough to make it start melting. Gold gets very pliable if you hold it in your hand for a very long amount of time. It's not that it won't melt in your hand, but it will get softer in your hand. It'll get closer to melting a lot faster than a lot of other things because it has a very low C. So, any questions about what C represents before we start using it? Okay, so everyone's boiled water before, I hope. So let's say that you have a stove and you are trying to boil a certain amount of water. You have 1 liter of water on this camping stove. The water begins at 70 Fahrenheit, and you notice that the stove takes a certain amount of time to boil it. My first question to you, second question comes later, don't worry about this yet. First question is, how much thermal energy does the water need to get up to its boiling point? Make sure these have ink in them. We're good. So, what is the first thing we should do for this problem? What's the first thing in general we should do?
Write what we know.
All right, so we'll sort of do both together. We'll write what we know, and we know that the initial temperature is 70 Fahrenheit. What will its final temperature be? 100 what? Water boils at 100 Fahrenheit? Okay.
I don't know.
So water boils at 100 Celsius.
Yes.
And already we notice these are different temperature scales, so we need to convert at least one of them. What should we convert to what? Yep, so Celsius is more metric friendly, so let's take our 70 Fahrenheit and make it Celsius. Just to remind everyone of the formula, if you start with Fahrenheit, you want to subtract 32 from it, and then multiply the whole thing by 5/9 to get your Celsius degrees. So approximately, what is the water's starting temperature in Celsius?
21.1.
Thank you very much. So that is our initial temperature in Celsius, and 75 or so Fahrenheit is considered room temperature, and about 20 to 23 Celsius is considered room temperature. So these do relate to each other pretty nicely. Like, I would look at this and expect the number to be about 21. So that's just a quick sort of thing you can do in your head to check your work. So this conversion makes sense. We're good to proceed. So we know our initial temperature, our final temperature. We know the volume of water. That's variable. Okay, volume of water is 1 liter. And we have time, which we're not using yet, but we know it, so I'll write it down. So that is everything that the problem tells us. Ignore 2.6 ounces, sorry, that's not relevant right now. Shouldn't have left it there. So, what we want, that's a funny looking T. What we want is the amount of thermal energy required. We need to know how much heat needs to be added. So, what formula should we use? Very good. So, Q equals MC delta T. So, do we have everything we need to proceed yet? Okay, so we're heating water. We need to know the way that water behaves when you heat it. So rather than just having to tap back the other slide, I will put the specific heat of water up on the board. This is a known constant that is considered true throughout the entire universe, and so you always have access to this number. Specific heat of water is 4,186. Again, one of the higher ones. You always have this piece of information. It is available to you. Go ahead and copy it in the corner of your notes. So, we do know the specific heat capacity of water. We know the change in temperature of the water. We want Q. What do we do for M?
Isn't 1 liter like 22.4 moles? Or am I just, is that just wrong?
I'm not sure about that for water.
Okay.
You're also overcomplicating it slightly. Now, that's not a bad approach. If that number is true, that's not a bad approach, but you then also need the molar mass of water. So that is a rather difficult way of getting the answer we want. There is a simpler one, which is the one I like to remember and will ask you guys to remember. The density of water is 1 kilogram per liter. So what's the mass of our 1 liter of water?
1 kilogram.
It's a kilogram. And so a lot of the homework will arbitrarily give you the volume of water, which is also, as long as it's liters, will also be the same number as its mass in kilograms. So fair warning about the homework. Of the problems I can pick, a lot of them give the volume of water just to be obtuse about it. But this is also a known constant. You always have access to this information as well. So that's everything we need to proceed. So our 1 liter of water has a mass of 1 kilogram. C of water is 4,186. And our delta T, change in temperature, is always final minus initial. We are ending at 100 and we started at 21.1. Again, because it's delta, we don't have to bother with kelvins here. So that's everything we need. We just need to start multiplying. And that should give us a nice, frankly large number.
Is that C of water, is that in grams or kilograms?
Oh shoot, you're right. Let me check real quick.
I think you got it in the grams number, but it's in kilograms.
It says kilograms, unless there's supposed to be dots there. No, that's a valid question because
I always remembered it 4.18, and I don't know if I just remembered it wrong.
Okay, it's 4.18 joules per gram. Because the gram is 1,000 times smaller, it needs 1,000 joules, sorry, 1,000 times less joules.
Okay, so that's right.
Does chemistry prefer grams because you're working with much smaller samples usually? Okay, so that's the difference there. That is a valid number, but that is the grams equivalent. Good question though, because threw me for a loop for a second there. Say okay though. So these are the kilograms version. You obviously need more heat for a kilogram than you do for just a gram. And because you need more heat, we're going to get a really big number.
It came out to be 330,275.
And what would our units be? Very good. So, a lot of joules. Many, many, many. Many times more. That's probably more than the energy in the food you eat. So, that is our answer to part one. We need a lot of joules to heat up this water. Now, if this was not water, if it was something with a much lower C value, then we wouldn't need nearly as many joules. So, it's good for life on this planet that the C of water is so high. It just is a little inconvenient when you're trying to cook spaghetti. So, that is our answer to part one. Part two, how many joules does a stove transfer per second? So, mathematically, what do we do with that question? Yep, so just the energy over time. We know the total amount of energy going into the pot, at least into the water. And for time, should we just plug in 4.6? Or what should we do with that?
Well, it's 7 seconds up there, so I don't know.
Oh, did I miswrite it? Yep, 4 minutes and 7 seconds. Oops. Thank you for catching that. I don't know why I wrote 6. So, 4 minutes and 7 seconds. How should we plug that into the question?
247 seconds.
Thank you very much. Everything wants to be seconds because that is standard unit. Wait, say it again.
47.
47. Thank you. I am just writing all the wrong numbers today. I'm sorry, everybody. So, that will tell us some amount of joules per second. That is the rate of energy transfer. So, what is our answer here again?
1,337.
1,000?
Yeah.
37?
337.
Okay, thank you. My ears aren't so great. All right, what would our units be?
Joules per second.
Very good. So that is the rate of energy transfer. Now, the reason I ask this question is it will come up in later parts of this and the next chapter. And the other reason is, for those who remember energy per second from 1500, what is energy per second equivalent to? What is the rate of which energy is used?
Can we phone a professor?
You can. Do you want me to give you a hint or do you want me to just tell you? Okay, it's power. Power equals work over time, which is joules per second, which is measured in watts. So this camping stove has a power output of about 1,300 watts, which It's a lot compared to, say, like a 60-watt light bulb, but that's because you're burning gas. Gas has a higher energy concentration. And so, again, the power output is just the rate at which the energy is delivered. So keep that in the back of your head, because we're going to talk about the rate of energy transfer specifically later in this chapter, and watts will come up again in the electricity stuff. Okay. So any questions on this particular question? That wasn't meant to be fun. Yes.
Why do we use what we did for N?
For mass? Well, we're told we have 1 liter of water, and the density of water is a known constant. It is 1 kilogram per liter. And so, if we have 1 liter of water, we can use the density as a conversion. So 1 liter of water is 1 kilogram of water. Kilograms cancel, liters cancel, that leaves you with 1 kilogram. So for water specifically, if you have some number of liters, that will have a mass of the same number of kilograms. So known assumption, you can also keep that in your notes. That knowledge is available to you for any given question. Anything else? Okay, so we're basically going to segue directly into a different example to make it a slightly different point. So, does anyone need like water or something? You need to rest. We're getting near the end, so I just want to make sure no one's mentally tired yet. You all have good weekends? I was actually out of town, so I didn't know we got stormed on.
Oh yeah, the storm was really bad.
I went running yesterday and just tree limbs everywhere, so I kept stopping to clear them off the sidewalk.
One of the high schools in my district that got like destroyed.
Ooh.
Kershaw?
Yeah.
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 It's like
Gone.
total. Like it's all the buses were like totaled. It just tore through the whole school.
Okay, I was in Augusta and Columbia, and it rained, but it didn't like tear down trees and destroy buses.
Yeah.
Holy crap. Well, glad everyone's okay. Hope no one's personal property was damaged.
My power went out for 3 hours.
When I got home, all my clocks were flickering. And then when I woke up Monday morning, they were flickering again. So I guess power went out over Sunday night to Monday morning too.
Yeah. One of my friends lives in the Highland Apartments, and hers was out Saturday night all night, and then it went out again Sunday night and Monday morning.
Good thing I wasn't here then, because I would have been on my computer and that would have been frustrating.
Yeah.
Okay, but hope everyone got along okay out of that and wasn't massively inconvenienced. Speaking of, well, energy more so than power. So, don't focus on the question yet. Right now, focus on the thing on the left. So, that is the point before we do the next actual problem. Energy cannot be created or destroyed. It has to go somewhere. It can change forms, it can change what has it, but you cannot obliterate it. So, if energy is being transferred out of one object, it has to go into a second object. If thermal energy is lost, then it has to be gained by something else. So this statement is sort of a before and after, but it is uniquely a before and after between 2 separate objects, 2 separate parts of a system. So, a second ago, we were looking at boiling water. This is the energy that was gained by our water. That means something else had to lose this energy, which was the heat given off by burning the gas in the camper stove. So the stove burned gas, the stove possessed then this amount of thermal energy over the 4 minutes and 7 seconds, and over that time, this energy was then lost by the stove and gained by the water. So all of these can be looked at in a lost versus gained sort of perspective. Now, Is everyone familiar with what these brackets are?
Absolute value.
Okay, very good. These are here because if one side is losing the energy, it is technically going to be a negative number. So its energy dropped, its Q should be negative. Conversely, this is gaining thermal energy. As temperature rises, its Q would be positive. So the absolute value sort of eliminates that inconsistency. Additionally, though, a second way to write it, which is the way that I usually do it, just out of instinct. So without these absolute values here, you have the issue of this side is negative, this side is positive. So an equally valid way of writing the formula, and the way that I do it, is if you add another negative sign to the Q lost, that makes it positive, and then everything equals each other, and you don't have a divide by zero kind of moment. So they mean the same thing, because if you slap the absolute values back on here, everything is still true and correct. So equally valid way of writing the formula, and it's the way I like to do it. So is everyone okay with this version before we proceed with the math? Okay, I'm going to erase some of this to draw a very poorly drawn picture. Why are my erasers always migrating? I say that like it wasn't me that moved it. Okay, so now we can pay attention to the question side of the slide. We have a small piece of copper, 50 grams. This is the copper's original temperature, 120 Celsius, and we drop it into 1 liter of water, which means 1 kilogram of water, and the water is originally at 21 Celsius. So, thermally speaking, what we have here is a system comprised of two objects. Copper's red, right? I can use red for copper. It's reddish. So, lump of copper. So our two object system is object 1, copper, object 2, water. And thermal energy is going to transfer from the copper out into the water, because the copper is hotter than the water. It has its particles on average have more thermal energy, and so when the copper particles collide with the H2O particles, thermal energy is going to net transfer into the water. The copper's temperature drops, the water's temperature rises. And this is kind of a smaller scaled down thing of what blacksmiths do for a living. And what we're going to see here is that due to the differences in the specific heat of copper versus water, that the temperature shifts are going to be pretty imbalanced. So, how do you think we should begin?
Isn't this a problem where we put like MC delta T equal to each other, and we do one as the copper specific heat and the other one as the water specific heat?
Correct, very good. So, we have one Q set equal to a different Q, and Q is equal to MC delta T. So instead of Q's, we can rewrite it as MC delta T equals MC delta T, but we just have to be specific about what side is what. So which object is losing thermal energy? Okay, so everything on this side, everything we replace this Q with needs to be of values from the copper. So we're keeping a minus. So Q equals MC delta T, so that needs to be mass copper times C copper times delta T copper. And then on the right side, the water is what must be gaining the energy then. So we have mass H2O, C H2O, and delta T H2O. So technically the same variable labels, but we're pulling it from the different sides, and so none of the numbers are yet equal to each other. So if we start plugging things in, we're keeping our negative sign to make everything balance. We have 50 grams of copper, but in physics at least, we like kilograms more, so all of our constants are in kilograms. So let's just convert it to kilograms. 50 grams is 0.05 kilograms. We do need the specific heat capacity of copper, which we know it's copper, so we can look up its specific heat capacity. That is a known value to us. So we just flip back to our table. I know my notes are on top of it, but in the units we're using, scroll down to copper, 387 is the C that we want. So I will go ahead and write that down.